Welcome, Woodstock physics students, and here's the third in a series of tutorials thinking about energy. And in this case, we're going to talk about energy, and we're going to talk about work done by various agents that can change the energy of an object. So we're going to define work here as it says on the handout that you've got, that work can be defined as the amount of energy that must have been given to an object in order for that object's energy to change. So in other words, work is equal to the change in the total energy of some object. We're going to be playing around with gravitational potential energy, elastic potential energy, and kinetic energy here. And in the problem set that you're working on, you should refer back to these formula to be successful. And we're going to take a look at a question number 10, which is on the back of your handout. So let's do that one together. Question number 10 is a problem about a slingshot used to launch a small pebble into the air. You pull back on the slingshot a certain distance. And of course, you're storing some elastic potential energy there. And then you let it go, and the pebble will go and leave the slingshot with an initial velocity of 13 meters per second. Okay? So there are a couple of different questions we can ask. How much work did the slingshot do on the pebble? What is the slingshot's spring constant? That would bring us back to this formula right here. Elastic potential energy is 1/2 k times x squared, where k is the spring constant. Okay. And assuming all of its energy goes into potential energy, how high will the pebble go? So let's take a quick look at these problems in order, okay? Well, what is the change, the total change in the energy of the pebble? It started out as 0, it wasn't moving, presumably, and then it was launched in the air at 13 meters per second. So now it's got some kinetic energy, which we can calculate right here. Ke equals 1/2 times the mass times 13 meters per second squared. And if you calculate all that out, you'll get 3.84 joules of energy. That is the work that the slingshot did on the pebble. Of course, you could also say that's the work that you did pulling the spring back with the pebble in it, but we can kind of break that in just about any way we'd like. But essentially, as we think about the springiness of the slingshot, that's how much work the slingshot did as it transferred that elastic energy into kinetic energy. So we're going to take that right away. We're going to take that idea right away and use it, okay? Part B, what is the slingshot's spring constant? Okay, the work done by the slingshot must have been the energy stored in the slingshot just before release. Where did that energy come from, right? If the pebble now has 3.84 joules of kinetic energy, it got that because the slingshot had stored that energy as potential energy. So we're going to take a look at that. All right, by using the elastic potential energy formula. Here it is. The elastic potential energy we're assuming is 3.84 joules, and it's 1/2 times k times the distance the spring, or in this case the slingshot, was stretched, so 0.85 meters, and that gets squared. And if you work that out and kind of work your numbers out, you're going to find that the spring constant is 10.6. A spring constant of 100 would be a much stronger and much more difficult spring to compress or to expand. A spring constant of 1 would be something much easier to expand and would store a lot less energy. So this is just a modest number here, but it would be our spring constant of 10.6. Last question here. And the last question is, assuming that all of the energy that the pebble has as it leaves the slingshot, assuming that all of it goes into potential energy, how high will the pebble go? Well, this is not an unreasonable expectation to think that as the kinetic energy of the pebble decreases, it's got its maximum value as it comes out of the slingshot, and as the pebble rises, it's gaining potential energy and losing kinetic energy. At its max height, the kinetic energy would be 0, and all of the original kinetic energy must at that moment be gravitational potential energy. So once again, that magic number, 3.84, has got to equal, that's our now assumed gravitational potential energy at some height h, okay? It's got to equal m times g times h. And once again, if we just are careful about our numbers there, we will get a height of 8.61 meters. Okay, so this slingshot will propel that pebble 8.6 meters in the air, which is something on the order of 25 to 30 feet. Okay. Overall, I just want to say that these formulas here will allow you to calculate different kinds of energy, and as one gets changed into another, we're going to idealize the situation, assume there's sort of no thermal losses or no frictional losses or anything like that. We'll make that assumption there, and we can kind of trace back and think about how different objects can work on other objects to change their total energies. Okay, hopefully that is a good start for you. I want you to work on questions on the front side of the page and be able to work those out. And come see me during the week if you need to get some tips. Okay, good luck.